Let's see one more type of paging scheme, that is hash page table. Okay, so in hash page table, that is used to handle the address space more than 32 bits, that is 4 GB of process size. Okay, so in this hash page table, okay, hash page table, we will use a linked list of elements. Okay, so in the linked list, the first element will be your virtual page number, VPN, virtual page number, and the second element will be value of the mapped page frame. So there is a page frame for this particular page number, and third one will be a pointer to next element, pointer to next element. Okay, so this particular page number, so this will be your page number, the first one will be your page number, the second one will be your frame number, and the third one will be your next element, third one will be your next element. And let's see the operation how it will be done. Okay, so the page number is hashed into a page table, the page numbers are hashed into a page table. That means each entry in the hash table contains a linked list of elements, a set of elements will implement with linked list. Okay, that is hashed to the same location. That means we will give this particular page number to a hash function, page number to hash function, and the same location will add. Previously we have given one location, now what will happen, there are multiple page numbers will be connected to one particular entry, because for the same page table entry there will be multiple locations, there will be multiple locations. See here what will be happen, there is a page number, so the CPU will generate a logical address, and that particular logical address will be given to a hash function. Okay, will be given to a hash function, the page number is given to a hash function, and it will generate a hash number, it will generate a number. Okay, that number will be given to some particular entry, so that there is a page number, okay, and the frame number and an entry here. Okay, now what will happen, this generated logical address, this generated logical address is mapped with this particular page number, then the corresponding frame number will be retrieved, okay, extracted. If this is not matched, then it will go to next list, okay, next element, and maps with this one, first compares with this particular page number. If there is a match with this particular page number, it will return the frame number. If this is also not matched, we'll go to next one, we'll go to next element in the linked list. Okay, so that's how the operation will be performed. If there is a match, we'll get the physical frame. If there is no match, we are moving to next frame and search for. Whenever we'll get it, then from that particular frame we'll get the desired byte of that particular address. Okay, so this hash table is suitable for 64-bit system, that is more than 32-bit system, that is the process size is very large, the process size is very large. There is one more type of hash paging, that is called clustered hashing, clustered hashing or clustered page tables. Okay, so here we'll use this particular cluster page table for 2 to the power of 64 bytes, that is 64-bit addresses will use clustered page table. Okay, so similarly hash paging, here each entry refers to maximum of 16 links, okay, 16 elements. Rather than one, we'll use 16 elements. A single page table entry can store the mappings for multiple physical page frames, multiple physical page frames. These cluster page tables are especially useful when the memory references are non-contiguous, and the memory will be scattered, of a process will be scattered to different places of the main memory. Okay, right. Now let's see one more type of paging technique, that is page table technique, that is inverted page table. So before going to inverted page table, there are some problems with page tables that we have discussed. What is that? Every process will have a page table, every process will have a page table, and this particular page table, the size of the process is more high, that is 32 bit and 64 bit. The number of entries in the page table is also increased. As we have seen the 32 bit, we have seen 1 million entries. Okay, we have seen 1 million entries. If the the number of entries are more, the amount of space required to store in the main memory is also more, and it will take a large amount of large amounts of physical memory just to keep track of how other physical memory is being used. Okay, that means if there are multiple page tables are there, this will take page table 1, and there is one more reference, page table 2, page table 3, and finally we will find one particular entry. Okay, that is frame number. In that particular frame number, the actual byte we need to retrieve. Okay, so maintaining this particular page tables in the main memory will take a large amount of space. So in order to avoid that, they have introduced one more concept called inverted page table. So instead of each process will have one particular page table, here the entire physical memory, that main memory, will maintain a table. Okay, we'll maintain a table. That means that the system will have only one table. System will have only one table, that is inverted page table, where each entry in the page in the main memory, okay, will be associated with one page number. Will be associated with one page number, that is the actual page that is stored on it. Okay, but in order to identify the page, okay, of a process, a particular process, okay, a page of a particular process, not only page number is required, we also require the process id of that particular process. Okay, so this particular process id, it acting as address space identifier. Address space. So now the logical address is actually divided into three parts. First one, PID. Okay, as we said, it is an address space identifier. Address space identifier. Okay, then followed by a page number and followed by offset value. Okay, so whenever the CPU generates a logical address, it will take the pair of PID and P, because see, there is a process P1 and have a page number 10 is stored in the main memory, and similarly there is one more process, suppose 5, P5, and the same, it also has page number 10 that is stored in the main memory. So when the CPU generated logical address 10, so it is P5 logical address or P1 page number, P1 page number or P5 page number, we need to find out. So that's why it is also important that we also maintain a process ID. Okay, so the logical, whenever the logical address is references, what it will do, we'll take first process ID, we'll search for process ID followed by page number. So we'll make a pair of these two. Okay, and search in the page table, inverted page table. If there is an entry found, we'll take the particular, we'll go to that particular uh, place frame and fetch that particular byte. If there is no match, then there is an illegal address access has been attempted. That means the corresponding page is not available in the main memory. The corresponding page not available in the main memory or physical memory. Okay. The examples of this particular inverted page tables, that is 64-bit UltraSpark and PowerPC systems. Also, there is a system called IBM RT that uses this particular page tables, inverted page table. But this particular inverted page table, even though this particular inverted page table decreases the amount of memory needed to store each page table, the problem here is it increases the amount of time to be searched for a page reference. That is, whenever the logical address is generated, it will take a lot of time to find that particular page in the page table, So even though systems will use this particular inverted page table, there is one more problem, is that they are difficult. Okay, they are finding difficulty in implementing shared memory. Implementing shared memory. First problem is, even though there is an advantage of size, there is space advantage. The amount of space is reduced to store page tables, but the problem is the time will be increased. The time to search will be increased. Okay. Then second one is, we are implement difficulty in implementing the shared memory. So that's why we are not using inverted page tables in most of the operating systems.